Okay, AP Chemistry students, this is a just brief presentation about bond energy. Um, you already had uh, talked about or did through a POGL understanding energy associated with lattice energy, which would be ionic compounds. This web video is going to be a brief video about bond energy related to covalent compounds or molecules. So when we're talking about a chemical reaction, we know that bonds have to break and new bonds have to be formed in order for products to be made. To break those bonds, the energy must be endothermic. So there has to be some type of energy put in. And if you recall from your first year course, that's typically called an activation energy. We will be discussing that more in chapter 12. New bonds are formed, and when bonds are formed, because of the potential energy then being lowered, the energy is released, and that is an exothermic state. So we can calculate that change in energy by calculating the delta H is equal to the sum of the bonds broken minus the sums of the bonds formed. And where D represents the bond energy per mole of bond, this will always have a positive sign. Now with this equation, do not get this confused with sum of the products minus sum of the reactants. This is for bond energy. You first have to break the bonds in a chemical reaction, and then you evaluate the bonds that are formed. In your textbook, you will notice that you have two tables, table 8.4 and table 8.5. These tables have a bond energy, so average bond energies, notice they're in kilojoules per mole. Table 8.4 is all for single bonded I guess there's multiple bonded compounds over here as well, but there's a whole variety. And then when you look at 8.5, you'll notice that they're for carbon single bonds, double bonds, triple bonds, carbon-oxygen bonds, single and double, and so forth. And these would be the bond energies that are associated with them. This table as well also has a bond length. And I guess it's not all that uncommon or really not that difficult to kind of visualize that the bond length for a carbon-carbon double bond would be bigger than the bond length, as you notice, for this carbon-carbon double bond that has a shorter bond length than a carbon-carbon bond. And you notice, look at the energies. The energies make sense too. A double bond is going to have more energy than a carbon-carbon single bond. So what we're going to take a look at, and this would be in your textbook, you'll want to look at the bond energy. This is on page 363 and 364. This is example 8.5 from your textbook. And here they're giving you a chemical reaction. Methane plus chlorine plus 2 fluorines will make a carbon difluoride dichloride compound, hydrofluoric acid and hydrochloric acid. And it says, using the bond energies listed in table 8.4, calculate the delta H for the reaction of methane with chlorine and fluorine to give Freon 12, which is that CF2Cl2 compound. Okay, so the first thing that you're going to do is you're going to take a look at your reactant bonds, and you are going to say, okay, there are 4 carbon-hydrogen bonds. There are 2 chlorine-chlorine bonds and 2 fluorine-fluorine bonds, and you calculate the total energy required for that analysis. And I'm going to just kind of make that small so I can get these all in here. Then we're going to look at the bonds formed, and you'll notice that you take a look at the bonds formed would be 2 moles of the chlorine-fluorine or carbon-fluorine and 2 moles of the carbon-chlorine. Calculate the energy associated with them, 2 moles of HF, 2 moles of Cl, and there you get your total energy released. Okay, so you have the energy required here, and then here you have your total energy released. And what will happen then, you can calculate the energy required to break the bonds and the energy, you can calculate the delta H by the energy required to break the bonds and the energy released when the bond is formed. You come up with a negative 194 kilojoules. Again, remember, energy can't be negative. That sign tells you that the reaction is indeed exothermic. All right, so another example would be something like this problem here. And let's see, I'm going to put a shade on this here so it's not quite so daunting the first time we're looking at it here. So here we go. We've shaded this up. And we're going to take a look at this equation. This would be a ethene, C2H4, plus ozone, making a CH3, C double bond oxygen, H, plus O2. Now, for the AP test, they'd probably expect you to remember what the structure for an ethene is. Recognize that this would have a double bond. The structure for ozone, again, too, they'd probably expect you to remember that. And if you're like, oh my gosh, this is very difficult, remember we haven't done yet in this class VSEPR and shapes of molecules. That's going to be happening. They wouldn't necessarily make you remember that is an aldehyde. They'd probably give you the structure of the aldehyde, but they would require you to know that structure of the O2. So now what you would have to do is you would end up having to look at your textbook or a chart. They would give you this data. They wouldn't expect you to just come up with this alone. You wouldn't have to memorize bond energy data. But you can see that you're going to, first of all, calculate the amount of energy that of the bonds broken, and then you're going to calculate the amount of energy for the bonds formed. And so when you take a look at this, let's see if we can get this bigger here. I'm going to get rid of the shield here. So when we get this a little bit bigger, you'll notice that the bonds broken takes 2,907 kilojoules of energy, whereas forming would take 3,239 kilojoules of energy. And then when we calculate that, you would end up with a negative 332 kilojoules per mole, that reaction being exothermic. Okay, so that is the extent to how you can calculate the energy associated with a chemical reaction for molecular compounds. Stay tuned because the next lesson will be on Lewis structures, and we will be doing that in class next.